Hello, my name is Lauren, and today my project team, Reagan, Terry, Catherine, Carolyn, and I, the Dream Team, are going to share with you our butadiene to styrene plant process design. The overall agenda for today is to share with you the key information for our plant design, then go over the economic analysis of this design, and going to conclude with some recommendations and an overall summary of our research. Just to give you a little bit of a background on our company, we are producers of ethylene, propylene, butadiene, C4s, and aromatics. As of late, the demand though for butadiene has started to decrease, which is obviously not a great thing for our company's revenue. So our team had done some research and found that styrene, which can be produced from butadiene, is expected to maintain a relatively strong demand in the market in the upcoming years. So in addition to this, we also found out that our company is looking to open a new plant with our regular production of butadiene, C4s, etc. in Taiwan. And so our plant is designed to be built into that Taiwan complex. As of right now, the design is made to operate at 8,400 hours per year at a capacity of 100,000 pounds per hour to yield a product of 99.9% styrene. So, just to go over briefly on the chemical process, what would happen is that we would take the butadiene from our regular plant production, and then it would be converted into vinyl cyclohexene, or VCHX. And that is very important because the VCHX is then used to produce styrene. And it goes through this oxydehydrogenation process that then produces the styrene. But of course, while we're producing the VCHX from the butadiene, cyclooctane is a byproduct, and that forms, so we're going to go over later how we work to remove that. And another couple of side products that are produced are the ethylbenzene, the benzoic acid, benzaldehyde, water, CO2. Those byproducts are produced from the process when the VCHX is being converted to the styrene. So we will go over that in more detail later about how we were able to separate that.
So for our project, we had hard specs that were required to meet, and then we had soft specs that were strongly suggested we meet. So probably our most important hard spec was of the product, which is styrene, to be 99.9% by weight purity, which we met. The other hard specs were all about the impurities and the maximum concentration they could be. They were given to us in parts per million by weight. So ethylbenzene, total olefins, oxygenates, and water were all of the impurities, and we were able to meet the spec for all of these impurities. We were below the max or at the max. So for the soft specs, the first one was the overall selectivity, which was supposed to be 78, and we met that. The selectivity is defined by pounds of styrene per pounds of butadiene. So the next soft spec was about the losses. So the losses of styrene and the losses of vinyl cyclohexene. And they were supposed to be at or below 2%, and that is of the amount that was produced. So we were able to meet the styrene spec, but we were not able to meet the vinyl cyclohexene spec. We were above the 2%. Later in the presentation, we'll discuss the trade-offs and the design challenges we had to encounter when deciding which spec to meet. And the last spec was the energy for distillation towers. That was to be below 2,500 BTU per pound styrene produced. We were also above this as well, and we will discuss this later.
So in addition to product specifications, we also had reactor specifications. For the VCHX reactor, the maximum temperature rise from inlet to outlet was 25 degrees Fahrenheit, and this is to ensure an efficient and safe reaction. The pressure drop was also kept to 30 psi maximum, and this is to ensure the catalyst works properly. In the oxydehydro reactor, the temperature rise was 50 degrees maximum, and again, this is to ensure an efficient and safe reaction, and the pressure drop in this reactor was limited to 25 psi. And the pressure exiting this reactor had to be 30 psi to ensure good catalyst performance. The oxydehydro reactor also had some specifications of the feed. Oxygen had to be limited to 20 mole percent, And this is because if the concentration of oxygen goes above this amount, we start having flammability issues. And also the heavy components were limited to 1,000 part per million maximum. And that's because if the heavy components go over this concentration, then we'll start having side reactions and we won't actually be producing as much styrene.
So, with these required specifications in mind, we were then able to further develop and design our plant process, as shown here by this BFD. Our plant process can be broken down into roughly 3 main sections. The first being the production of vinyl cyclohexene using the VCHX reactor. Then the second portion being the oxydehydrogenation process, where vinyl cyclohexene is being converted into styrene. And then the last portion of the process of just purifying the styrene product, removing anything, and storing it. And all of this is made possible with 2 reactors, 2 storage tanks, 4 distillation columns, a 3-phase separator, 5 pumps, 6 heat exchangers, and 2 compressors. So, while looking at the first portion of our process, we have our butadiene stream coming from our Taiwan complex. This stream is then sent to the VCHX reactor, and coming out of it is VCHX, of course, but also some remaining butadiene and impurities. So we then send that stream into a distillation column where the butadiene and impurities are recycled back into the feed, of course, obviously, so that we can just reuse some of our byproducts. And then the vinyl cyclohexene and cyclooctane, which is, again, that side product we were talking about before, comes out and goes to the next portion of our process.
Okay, so starting at stream 9 coming in, which is predominantly vinyl cyclohexene and cyclooctane, we take it into a distillation column, removing cyclooctane out of the bottom in stream 12, and vinyl cyclohexene comes out the top, stream 11. So then we continue on with the process, and at this point we want to mix in our inhibitor, which is TCB. The point of the inhibitor is to prevent styrene from being polymerized. So right now it's in a storage tank up here, just at standard operating pressure and temperature. Comes down, we mix it with oxygen as well as the recycles, and then it goes through a heater and a compressor in order to make it into the appropriate temperature vapor phase to go into the reactor.
So the oxydehydro reactor is operating at 700 degrees Fahrenheit. And then the product stream coming out of the reactor is mainly styrene and has to go through a compressor and a cooler to get it at optimal conditions so that we can separate out the styrene and the impurities. So going through the 3-phase separator, out of the liquid phase is mostly styrene, and then aqueous phase is what we want to recycle. So the aqueous phase is made up of mostly water and VCHX. So we purge out some of the recycle stream just so that it doesn't accumulate, and then we put it through a pump and a heater to get it at the optimal pressure and temperature, and then we recycle it through. So our first distillation column after styrene is created is used to separate out VCHX, ethylbenzene, and N-pentane. N-pentane comes out the vent, while ethylbenzene and VCHX come out the distillate. Styrene comes out the bottom and flows into our next distillation column, which separates out benzoic acid and benzaldehyde. These 2 impurities come out the bottoms, while styrene comes out the top and into the storage tank. The storage tank has a cooling coil in it to keep our product maintained at 50 degrees Fahrenheit.
Another side process that you do not see from our BFD presentation is a catalyst regeneration system. During the operation, the coke forms and gets laid down in the catalyst pores. Due to this fouling, the catalysts in V100 have to be regenerated every 30 days by coke burn-off in a steam-air mixture. The coke deposit amounts were assumed to be 1% of the catalyst weight after 30 operational days. The total regeneration operation including shutdown, purging, burnout, and startup takes about a week. Due to the flammability safety regulations, only 2 weight % maximum of oxygen is allowed in the steam and air mixture. It was determined that having an operating reactor and 100% spare reactor will be the most ideal to minimize the production downtime and the capital costs associated with catalyst regeneration after a careful economic analysis. The typical regeneration requires a fired heater, knockout drum, cooler, and a water pump. All the equipment listed here has different sizes, and of course individually they have all different costs. For the inner boundary limit, or IBL, the cost of distillation columns include the cost of the column itself, 2 reflux pumps, 1 reflux drum, and 2 heat exchangers per column. For the reactors, the cost of 2 units of the VCHX reactor and 2 units of styrene production reactors in parallel are accounted. As I mentioned in a previous slide, purchasing another 100% operating capacity VCHX reactor is necessary for the reactor replacement during a catalyst regeneration time. The cost of primary tees and control valves for processing mainstream is featured here. The catalyst regeneration includes the cost of a pump, a drum, and 2 heat exchangers needed for the system. As a result, the total IBL was calculated to be $152 million. The site development will occur on an existing company space adjacent to the BD plant in the Gulf Coast of Taiwan. Referring to the OBL bid costs obtained from the similar project completed by the company in the past, the 2016 projection costs for OBL were calculated. 3% escalation per year since the year that the bid was obtained from was assumed. For the OBL costs with the dependence on bid capacity, the ratio of the bid capacity and the actual capacity was multiplied to the bid cost in order to take account for the differences in capacities. The total OBL was calculated to be $240 million. Overall, the capital estimate was determined for 100,000 pound per hour styrene capacity with January 2019 as a project startup date. OBL is higher than the IBL because of the high utility costs and raw material and product storage costs due to a high capacity. The catalyst cost needed for the startup of the plant, the project team cost, and startup cost was included into the total plant cost. 9% of the escalation and 20% of the project contingency was assumed as well. As a result, the total plant cost was calculated to be $643 million.
The raw materials has the biggest impact on our costs, especially butadiene due to its high flow rate. The catalysts used are also very expensive, which leads to a much higher cost. The process requirement for the catalyst is based off of the need for every 3 years, since the life of the catalyst, even if it is regenerated, will not last past then. The byproducts created are collected into a waste stream, which feeds to our complex's currently existing waste treatment site in an adjacent butadiene plant. Therefore, no costs are associated with our byproducts. Since we are not intending to sell any byproducts for this base case, we do not have any byproducts credit either. The total cost for raw materials and waste management is $1.3 billion. As the stream temperature increases from 200 degrees Fahrenheit, the percent of styrene being polymerized increases significantly. Since the styrene production reactor is operating at 700 degrees Fahrenheit, in order to prevent all of the styrene produced being polymerized right away, the polymerization inhibitor is added to the styrene production reactor. TBC is the most common styrene polymerization inhibitor in the market in 2016, and only 10 to 15 ppm is needed in a stream at all times in order for TBC to be effectively working as a polymerization inhibitor. After the styrene production and purification steps, the styrene product is cooled down to 50 degrees Fahrenheit in a storage tank in order to eliminate any chance of polymerization during storage. Utilities also have a large impact on our plant costs. They total in $177 million. The fixed cost associated with our plant total is $31 million, since we will be needing about 40 operators, 10 people per shift, and 15 managers and HR personnel. This total also takes repairs and maintenance, property tax, and insurance into consideration. The selling, general, and administrative expenses, or SG&A, total to $11 million. Cumulative cash flow is negative $12 billion due to not having enough sales revenue of our product to outweigh our capital and operating costs. The net present worth of our project is also negative, totaling to negative $3 billion due to this issue. The internal rate of return is negligible since our project only generates negative cash flow during every year of operation. In order to meet the minimum requirement of 15% rate of return, we would need to sell styrene at $2.05 per pound, rather than the current market price of 64 cents per pound, which is simply not feasible.
Now that we have gone through the general plant process information and our economic analysis, we wanted to share with you some of the outstanding issues with our current design, such as the equipment and material costs. The size and duties to run some of the equipment are very high. The distillation columns, for example, they have a very large diameter, something that is too big for all of them to be, and that is caused because of the vapor volumetric flow rate. So we would need to do additional research to figure out how can we optimize those distillation columns. In addition to the columns, the heat exchangers are impossible. We would need to potentially design additional heat exchangers. In other words, we would need to do research to see if we could add other heat exchangers in series to help with the large temperature difference in the process streams and making sure that that temperature difference could be achieved. And lastly, with the equipment, that is, the compressors currently run at a very high horsepower. So we would want to potentially do something like the heat exchangers and look into maybe having multiple compressors in series to see if that would help with the process stream. And then for the economic portion, the raw materials are priced very high right now. And so in order for our company to have a positive cash flow revenue, we would need those costs to somehow go down. So to recap, although we successfully convert butadiene to styrene, we have estimated the capital cost of $643 million and a total cash cost of $1.5 billion, which unfortunately creates a $1.3 billion loss for our company. Even though we do produce styrene and it is predicted to stay, in a strong demand in the market, our estimations showed that the return from producing and selling styrene would not be feasible since we would need to sell it 3 times the current market price of styrene. So, we hope that we were able to share with you our research and concerns for this butadiene to styrene plant project. Should you have any additional questions, please feel free to contact the email at the bottom of the slide here, and thank you for your time.